this circle here. This circle is the top circle because he's touching all the other ones. Is that clear? And then the dual again will be a hexagonal pyramid because you have 6 triangular faces all touching a single hexagonal face. So that's what the red guys are, the dual. And again, when you act by Mobius transformations, this is the packing that you get. And maybe you don't believe me, but if you look a little bit more closely, you get integrality. Now, let's look at the bend matrices. So the bend matrices that come out will be 7 by 7 matrices. 7 because there are 7 vertices of a hexagonal pyramid. But they're rank 4 because they're circle packed. So it's 7, so there's some choice here. And you can't quite make them all integers, but you can make them all, at least for the polyhedron itself, you can make 6 of them integers, and the last one will have these denominators 3. And the funny thing is, when you take multiples of these matrices, you see these guys all are multiples of 3. So those denominators 3 don't grow. That's what's responsible for the integrality. And by the way, for the dual packing, all of the matrices are also integral. So you should start thinking that maybe this thing is super integral. But then you look at the Gramian, and the Gramian looks really good. These are all integers, these are all integers, and then on the off diagonals I have some square root 3's, but again I just get them twice as I go around any cycle. So it's arithmetic, right? There's a denominator root 3. You do this one twice, you get 2/3 or 4/3. You're not allowed to have 3's in the denominator for arithmeticity. So what's going on is that this piece of so if you think about this non-arithmetic group as a lattice in hyperbolic 3 space, there's a piece of it that's acting discretely and integrally. There's another piece that's also acting integrally and discretely. But when you have the two together, so these other matrices, which I didn't write down for you, don't have this property that these entries are divisible by 3. And so when you start playing between the dual and the original polyhedron, these 3's start to build up. And they build up forever. So that's why, so this is non-arithmetic, and this is why it's a type of Deligne-Mostow example, because they were looking at S-arithmetic groups, which, how do you construct a non-arithmetic group? Well, you make an S-arithmetic group, but then you force it to already be a lattice in the first factor. It's supposed to be dense in the first factor if it's actually a lattice in the S-arithmetic group. So this is an example that's like that. Okay, so I'm out of time. Let me stop this. Thank you. This is how we came to the conjecture. Okay, so what should be happening is that if you're super integral, it should be coming from, there should be some realization of these bend matrices, which is completely integral. And if that's the case, then that should itself be, I mean, it's a conjecture, right? So I'm telling you what I think should be happening. If that's the case, then it should be forcing the Gramian to have the Windberg criterion. So that's what we would like to show. And at the moment, we're doing it by example. We're plowing through all arithmetic groups known to have reflection, to be commensurate with reflection groups, and seeing which of them support sphere packings. So we have a lot more examples than what I showed you, but the general theory is finally forming. And the right question seems to be not integrality, but superintegrality, for exactly this reason. Jeff? So right. So we have this group gamma twiddle, right? It's a subgroup. It's a subgroup of O Z adjoin a third. So what I would like to do is see it as a lattice in OQR cross OQ Q3. So these denominators 3's, if you put it like this, then the three denominators that are ruining your integrality aren't ruining anything, right? That's what it means to be S-arithmetic, is to be a lattice in here. But this is not a lattice in here, because it's already a lattice in the first factor. That's what these Deligne-Mostow examples of non-arithmetic groups were. They constructed S-arithmetic groups, which already were lattices in the first factor, and hence had to be thin in the product. So it's actually a thin group of the S-arithmetic group, because it's already a lattice in the first factor, and that's what makes it non-arithmetic. If that makes sense. Yeah. So you're asking about the Descartes theorem, the relation between the bends. The Descartes theorem is nothing more. So we have this Gramian, which is there were some entries that are forced upon us, and then there were other entries that came out of the proof. The Descartes theorem is nothing more than the 1-1 entry of the inverse of this piece of the Gramian. So in the case of the Apollonian packing, you had -1s and then 1s everywhere, and there was nothing indeterminate because it's a tetrahedron. So the inverse of this matrix is actually itself, and the 1-1 entry is, if you work out what this form is, it's the sum of the squares minus half the square of the sum, equals 0. And it equals 0 because the inverse Gramian is related, so there's the bend. If you take the bends and you let and you measure them by the inverse Gramian, not the super Gramian, but the inverse Gramian. So this is the bend column vector. Transpose. So the transpose of this column vector will be Q. And Q, well, it'll be the 1-1 entry of Q. And if you recall, Q had a 1-1 entry of 0. So that's why the sum of the squares minus half the square of the sum is equal to 0. Now, if you go to hyperbolic, if you pack not the real plane, but a sphere, or pack hyperbolic space, then Q changes, and then the sum of the squares minus half the square of the sum will be -1 or positive.